Hello? I don't know, it's very weird. Yes? Sa. I don't know what people say in microphones. I've never done this. Yes, okay, thanks. All right, so types and terms, fuzzy logic. So we come up with this kind of nice square. So when we have binary stuff and we have proposition kind of things, you have 0 and 1. And then when you go to types, it's the same way as you go from 2 to sets. So instead, when you go from binary to fuzzy, we can kind of work with the unit interval, and then we can generalize that. But in this direction, just go, OK, from 0, 1 to the unit interval. Then what do we put in the last square, which is the one that we are looking for? We just consider sets with a valuation with values in the 0, 1 interval. So this will be the kind of the line that we follow. So from 0, 1 to sets, and from 0, 1 to the unit interval. OK, so first, I'm going to tell you what structure we consider that is interesting to us in the unit interval. So we consider a commutative monoid such that it's ordered with a partial order that respects the monoid operation. And it's unitally bounded, meaning that the top element is also the unit of the monoid. And we ask that it's complete in a sense of the category theory-like sense. So we have an exponential object or an internal OM in the monoid, with respect, of course, of the monoid operation. And we call that the internal home of M and N. So I'll give you some examples. So 2 is an example. So we've been doing something good. The unit interval is an example. So I think you'll be surprised of this. Also, if you consider a topological space, you can consider open sets on that. And these 2 is a commutative order monoid. If you consider this particular commutative monoid, which is introduced by Lovier, so you take the closed interval 0 to infinity with reverse order and addition and the 0. And actually, it's true that every commutative unital quantile is a commutative order monoid, and so in particular, every complete Heyting algebra. And actually, they're also bounded and complete. And I'll give you what it means in the context of the unit interval. So you can define kind of this right adjoint to multiplication, would be some weird sort of division. So we say that the internal OM of M and N is the minimum of the fraction, and we can define this fraction to be exactly 1 when M is 0. And of course, in a quantile, you can just use the sup of the set. All right, so we now know what structure do we need on our unit interval. Now we need to go from this structure to sets with values in this structure. So the category I'm talking about is sometimes called set M, and these are sometimes called fuzzy sets. You have many, many possible categories of fuzzy sets, but what I mean by this is just a set with evaluation taking values into the underlying set of the monoid. And morphisms are just functions that preserve the order. So very easy. And in the context, for example, if we consider M to be our unit interval, it just means that every set has a particular value attached to it. So we have a set, and we can kind of think of these as a membership degree or something. So we started from this, and now we're here. So we have something kind of being our fuzzy values, and we have something will be our fuzzy types. But I've been talking about type theory, so I need to kind of detail how do we go, how do categories relate to type theory, and how we can use that to do fuzzy types as we have been trying to do. So there is it's a close correspondence between type theories and set categories, and I'll explain this in a while. But our claim is that, well, okay, so if we want to do fuzzy type theories, we just use set categories. And so we kind of do it backwards this time. So I'm going to tell you what happens in the first line, and then we give a categorical definition, and inside the definition, we read this new type theory that we need. Yes. Yes, sorry. All right, so we enrich the category, read the type theory, find the theory that we need. All right, so enriching. So actually, both M and set M support monoidal structures, so we can use them to enrich stuff. In particular, set M will be the one that we're interested in. And so we can, the monoidal product of two M sets is as the underlying product of the sets, and as the value, the product of the single valuations. And the I is simply the singleton with constant 1. So it's very, very easy structure. This means that we can use it as enrichment. So for example, what happens, we can enrich, well, I mean, the structure on M is quite trivial, I think. So for example, we can enrich in 2, but this is just very simply kind of an order-like situation. We can enrich in I. This is also not what we need. So this is maybe why we need to use M sets, and we cannot use M straight, because this is just kind of an order, but the order has some value alpha. This is not what we need. We need to be able to have multiple values relating to different objects. And in particular, I said that L was introduced by Lovier, and when you're reaching L, these are called Lovier matrix spaces, and you can see that actually the composition that I'll describe will be just some triangle inequality. But let's look into the one that we need. So when we enrich in set M, what we find is that we can do some composition, and that composition has to respect the order. So basically, the product of the values is below, the value of the composite is above the product of the single evaluations. And of course, the identity has value 1. All right. So now to the relation between categories and types. So I'm going to use the notion of display map categories. There are many, but I think this is the easiest to understand. It's the one that we use because it's very heavily map-based, let's say. So a display map category. So now we're back to set enriched categories. So a map category is a pair CD, where C is a category and D is a class of morphism called displays or projections, such that C has a terminal object. So that will be, think of this as our empty context. And then for each projection and each map, there exists a choice of a pullback of the projection along the map. And these you can think of as substitution. This will be what we will look at very carefully too. And then D is closed under pre and post composition with isomorphism, which is just a technical result. So basically, what do we mean by this? Now how do we relate a display map category to a type theory? So each projection would be a type in a context. And if you have a projection, you want to read the context of the type, you just read the codomain. And terms will be interpreted to be sections of such projections. So for example, so in this case, we have PA, which is the type A. It's in context gamma because we read its codomain is gamma. And S is just a section of the projection. So all terms will be collected as sections of the projections. And as I said, the substitution will be pulled back along the projections. So in the sense, we will often consider S above to be actually a section. And so this will be like substituting the term into the type that the vertical projection is in. All right. So now let's go back to our intuition and see what axioms do we need to put in this new category. So we can think, our point is to think of a single set M category to be an agent in our system. And then, as I said, a context would be like a collection, like an ordered collection of beliefs, each depending on the ones before. A type would be thought of as a belief, and a term would be a proof or a reason why we believe something. Now, we want beliefs to be definite, so we don't want fuzzy types, but we want reasons to be fuzzy. So we want terms to be of some kind of fuzzy value. So non-fuzzy types, but fuzzy terms. So this is where we give our definition. So a fuzzy display map category is a pair CD with C, a set M category, D, a class of morphism, such that C is a terminal object. But now we cannot do pullbacks. We need to do weighted pullbacks. And I'm so glad that Luca thought about this, because I don't have to now. So we'll see that what it means in our context very briefly, but it's the same definition, we're just in a rich setting, and we substitute pullbacks with weighted pullbacks. And then, as I said, we need to ask that types are not fuzzy. So we ask that the value of each projection is the most possible value, so 1. Okay, so sections. So we say that S is an alpha section of PA if it is a section and its value is at least alpha. So nothing interesting here, but this allows us to show our first rule. So if we have that in context gamma, S as value, S is a proof of A with confidence alpha, then it's a proof of A with confidence all possible values below that. Not very interesting, but it allows us to show that we can, when we know something with at least some confidence, then we know it with also all lower confidences. So now I'm gonna show you what happens with calculations in the case of the unit interval, but just because it's easier, you can always extend it. So weighted pullbacks. So I'm gonna give like a very, very, very basic explanation of what it means in our context. So basically, when we ask for a pullback, we ask of an object and 2 maps. So these are the data, such that for any other pair of maps, there exists a unique map in that direction. But now we have maps, and each map has a value. So first, what do we ask of the 2 maps that come out of the object we start from? And also, when we have another pair of maps with values gamma and delta, what will happen to the universal map induced by the universal property of the weighted pullback? And that will be something depending on alpha and beta, which are the datum, and then also gamma and delta would be part of the datum. So as Luca was saying, if we only consider regular pullbacks, this is no use of us, because now whenever we substitute, everything collapses to 1. So we need to pick interesting weights, and interesting weights will be that appear in the span on top of the maps of alpha and beta value. All right, so there is something here, weighted pullbacks. I'll tell you what happens in our case. So we ask that the weights are actually just preserving the value. So whenever we pull back a map of value alpha, we want to be able to find a map that is at least value alpha, because we want our substitution to be conservative in some sense. And then if we have maps S and T of value gamma and delta, of course, the right adjoint will come back again. And you can do some calculation and see that the definition of the weighted pullback gives you this property. So we have that the value of the universal map would be the minimum of 1 gamma over beta and delta over alpha. So kind of looks nice. And now, finally, to the rules. Yes, I have still 10 minutes. So these are our rules for fuzzy type theory. So as I promised, we give this definition, and we read into the category some rules. So first, let me show you what the rules are, and then I show you how they can be interpreted. Where do they come from in our category? So we have our empty context. We have the context extension. So that is pretty easy, because each time you have a projection, you do have a codomain, but you also have a domain, and that domain is another context, and then context is the extended one. And then we have a variable rule. So I need to point something out here. So if we have a context gamma A delta, then we can always recover a certain term of type A, and this term will have the outmost possible value. But this does kind of make sense. Notice also that there is something strange. At least I've been asked this a while. So if you see all free variables appearing in contexts are not value, but the reason for that is that they're actually just objects, while what we're interested in is like the right-hand side of the turnstile symbol. So we're talking about judgments. So that is judgment with actually certainty 1. Then we have our conservativity result. Then we have 2 weakening rules and 2 substitution rules. And we can prove that a fuzzy display map category is sound and complete for the rules above. So I'll show you just a few ones. So the variable rule. So remember that the variable rule is saying that out of a context, we want to be able to get back a variable, so it will be a section, and its value has to be 1. But suppose we don't know that. Okay, so we start from, and for the purpose of this, we just consider the delta to be just of a single type, but it's no problem if it's just you can see that it iterates very well. And also, this is where I'm pedantic because there's some subtleties here. All right, so we have gamma, A, and B. So what it means is that gamma is a context, A is a type in context gamma, hence there is a projection PA from gamma.A to gamma. B is a type in context gamma A, so there is a projection PB from gamma.A.B into gamma.A. And so we have some sort of situation like this, and now we want to be able to provide a section of this projection we have just described. So we do our pullback. Remember, it's a weighted pullback. And now we can paste the identity here and a projection here. You can see that it all commutes. Remember that projections have value 1, so everything there has value 1. And so we can find actually a section of the desired map. Now, as I said, everything is 1, so the value of this section is 1. And now this is where I'm pedantic, because as you see, it is not really a section of gamma.A.B in the sense that the second A, now I need to point this. I'll try Andrea's method. I don't know, yes. This second A is actually not the same A as this one because they have different contexts, right? So you can see that this A is in context gamma and this A is in context gamma AB, all right? So there'll be 2 different projections. And so this is what I wrote down here. But usually most people don't care about this because it's kind of the same type still. And the reason is that this is actually a weighted pullback and we can provide a section of this kind. Substitution, okay. You see that it kind of works in a similar way. So now we have a type B in context gamma AB, gamma A delta. So it means that we have iterated projections that tower up in this way. And we have a term of this, a term little a of type big A, and this has now value alpha. So we want to be able to substitute and find B of A in context gamma delta A. Again, this is just an iteration of pullbacks. Because first, we do that substitution, we find the context that we need, and now we need to find this type B. So it's clear that the type B will be here. I'm not tall enough, but you can imagine where it is. Because that is now on the lower part, you can see that you have the correct context. And actually, you can compute it. Also, no, I'll talk about it later. Okay, last, substitution for terms. Again, this is a situation where we're at, but now we have also a term B, little b, in that context. And now we need to do some calculations, right? So we have little a that has value at least alpha because it's an alpha section. And then when we pull it back, we find that the value increases. And now we kind of use a similar technique, consider the identity, consider the lower part of the composition of the two. And again, we find a section of the desired projection. Now, we want to be able to tell what value it is, but with this, we just need to do a computation. And we find that actually the value is above beta. So it means, So it means that so when we substitute there, we find a new term, and its confidence will be still the same. And I know there may be a question about this, but I'll come back to that in a second. Yes, no, I'll do it now. Yes. Okay, grazie. So I've been asked, oh, there's many slides here. Okay, yes. I've been asked, isn't it weird that, the confidence still is the same throughout all these structural rules? And actually, as Francesco was, we were discussing it a few weeks back, and it actually is not, because they're structural rules. They're not supposed to change our confidence in anything. We're just combining stuff, but not really doing anything. So it's okay that the confidence is preserved. Of course, now we want to extend this theory to involve connectives and type constructors. So that will change, actually, the confidence, of course. But it makes sense that these don't change in our theory. All right, let me get back to the end. But yes, back to our interpretation. So a SELM category is an agent. A context is a set of beliefs. A typing context is a belief. And a term is a proof of the belief. But now we can read more into our category. So for example, we can read maps from 1 to C with confidence, the top element, to be kind of tautologies, because they come out of the terminal object with the most confidence. And so these will be the things that we can interpret to be tautologies. If we have another object and things, we can go out of that with, again, the utmost confidence. We can interpret them to be facts that can be deduced or by E. And then if we weaken it, so we can interpret arrows that go out of E, stands for evidence in our mind, with confidence alpha. You can think of them as things that can be deduced by E with confidence, at least alpha. All right, so what next? We need to deal with definitional equality. It's not a small problem. We have a few ideas. I can tell you about that if you're interested. Then we need to study constructors and the connectives. See what happens because we have this general definition, but it might be interesting to consider what happens when you actually interpret M to be different, like, for example, as the L introduced by Levier. And then finally, I promise you opinion dynamics. So there is some work by Hansen and Gerst that does this with sheaves. So we need to extend our theory to include this as well. And yes, so some references, and I want to just add that, as I mentioned, this is a part of the joint school project, and it's a school for students and PhD students. So if you're interested, be careful, because the deadline is January 9th. So maybe if you yourself are interested, or if you have any questions, come up. And I think it's a nice opportunity for students. I'm done.
So thanks, Greta, for the nice talk. So is there any question?
Thank you. Really, really interesting talk. My question is this different / related to quantitative type theory? Because it has the same decoration on typing judgments with elements in a monoid, and it seems the typing rules are really similar.
I don't know about that, but the person that suggested this project does. So I think I need to study more about it. But if you have anything that I can read on it, of course.
All right, thank you.
Thanks for the talk. So I have two questions, actually, but maybe I'll start with the first one. I guess there are other choices for the arrows of set M.
Yes.
So what happens with these other choices? Like if you take the other inequality, for example, or the strict equality, like the preservation of the valuation.
Yes. So what happens when you reverse the order?
For example, like have you tried to see?
Okay. So I think the thing is that you want deduction to be conservative. So when you do something to your judgment, you don't want it to be less informative than before. So I think it could work, but it goes in the wrong direction for the deduction in some sense. As for maybe you're thinking about functional relations, that is something that we're looking into, because as I mentioned, we need to find a way to do definitional equality. And so the most obvious choice, at least to me, would be to have sets which will also the equality predicate to be valued. And so you need to change your arrows, and so it changes things a bit. I don't know if that answers the question.
Yeah, yeah, thank you. And the second question is about the universe. Have you considered what happens when you have if you want to introduce a universe? Because in that case, the types becomes terms.
Yeah,
and so they become fuzzy. Or
yes, actually, we had quite a discussion about this, because I too believe that types should be fuzzy. So it's really, it doesn't do much in our theory that you asked that. I mean, it doesn't change a lot about our interpretation if you consider fuzzy projections. So it's not really a problem. The thing is that when you do, of course, when you do pullbacks, you want to have some kind of pullback pasting property. And so in the case of weighted limits, the composition should be kind of conditional to the fact that you can compose the pullbacks. So that changes a bit. But other than that, it works fine, I think.
Yeah, also, just a last comment. I think that your substitution rule for types would be more natural if you allow the types to be fuzzy.
I agree with you completely.
Okay, thank you.
Thank you, Jacopo.
So if there are no more questions, so I ask one just because I am curious.
Yeah.
So have you any idea of how difficult it is adding fuzzy assumptions in your context? Because I mean, my understanding of a context is the beliefs of an agent. So yeah. I think it's reasonable to have fuzzy beliefs of an agent.
It's a good question. I think this is probably not the easiest way to do it, but I think it should work if you use double categories. But I've been trying to read about enriched double categories, and it's not very easy. But if you do use double categories, in some sense, you can keep the two together. So you can kind of have some identity map, and you can take the value of that identity map to be the kind of the fuzzy value of the premise of the context, because now you have a map between a context and itself, right? And this is allowed because you have some kind of or horizontal or vertical direction, and so you still have maps. They can be valued, and you can consider the value of the identity as the value of the premise in some sense. But I'm not sure this is the easiest way, and we haven't thought about it. No.
Okay, thanks. And no more questions?
Yes.
Sorry, I can't resist asking this. So you interpret the internal home as this like minimum of the fraction in one, I think in the interval poset, right?
Yeah, it's not an interpretation. It's like the right adjoint to the multiplication.
Right, because there's also this thing that 0, 1 is isomorphic to like infinity 0, so 0, infinity the other way, through logarithm.
Yeah.
Does that give you this same thing?
I think so too.
All right, cool. Thank you.
Okay, so I think we stop here. So it's time for lunch. I think it is an